Hello, ladies and gentlemen. My name is Janet Kelsey of Separation Science, and I'd like to welcome you all to our latest webinar in collaboration with Marks International. Our topic today is simplifying GC-MS sample preparation for product and material testing. Let me introduce our presenters for today's webinar. Caroline Wooderson is the Marketing Development Manager for Thermal Desorption at Marks International, having completed her chemistry degree at Cardiff University in 2004, followed by a PhD in organic chemistry. As part of her current role, Caroline advises manufacturers, test laboratories, and research institutes on equipment needed to monitor indoor air and study chemical emissions from materials used indoors or in vehicle interiors. Caroline also participates in ASTM and CEN standards and regulatory committees relating to this area. Aaron Davis is the Commercial Marketing Manager for Thermal Desorption at Marks International. After graduating from Cardiff and Monash Universities with a PhD in chemistry, Aaron has worked in industry as a process and product development chemist, GC/GCMS product specialist, before finally focusing on his passion for thermal desorption. In his role, Aaron assists customers and partners on the effective use of thermal desorption for simplifying sample preparation and the benefits of using alternative carrier gases, such as hydrogen and nitrogen, to helium. And so, without further ado, I'll turn the presentation firstly over to Caroline.
Thank you for the kind introduction and welcome everyone. Aaron and I are really happy to be here today to talk to you about simplifying GC-MS sample preparation for product and material testing. Specifically, we'll be discussing the use of innovative microscale chamber systems coupled with thermal desorption GC-MS that enables robust, reproducible analysis of trace volatiles and semi-volatile compounds for a wide range of applications. Just a quick bit of background information on who we are. Marks International are global leaders in thermal desorption, which is a versatile pre-concentration technique for gas chromatography. It's used to analyze volatiles and semi-volatile organic compounds from solids, liquids, or gases. We're part of a group of companies dedicated to harnessing application and engineering expertise to improve all aspects of the gas chromatography workflow and deliver better business and scientific outcomes for both research and routine laboratories. The release of chemicals from products and materials has been at the centre of increased scrutiny from regulators, industry and consumers alike. Concerns over the effects of volatile and semi-volatile organic compounds on human health, consumer comfort and product performance are increasing. Analysts need a robust and reproducible approach to sample these emissions from a wide variety of materials and products. To be able to look at GC-MS, to identify the compounds and answer such questions as, what is that smell? Is my product safe? Is there anything toxic in my home or my car? How can I detect a harmful chemical from a material? During this webinar, Aaron and I will address the use of an innovative, robust and cost-effective sampling device, the microchamber thermal extractor, combined with the powerful analytic capabilities of thermal desorption, gas chromatography, mass spectrometry, with several case studies to highlight the implementation of this versatile sample preparation. And this will cover a wide range of applications, so hopefully there'll be something for everyone. Scientific publications and mainstream media, even platforms such as TikTok, are frequently highlighting concerns around household items, clothing, cooking devices, and the effect that the emission of chemicals from these may have on human health. As mentioned during this presentation, we will introduce some sampling and analytical techniques which greatly simplify the process of identifying these compounds. I'll pass over to Aaron now to talk through some of the products and the theory behind them.
Thanks, Caroline. So from the sampling side, the accessory we've conveniently used here is a microchamber thermal extractor, typically referred to as a microchamber. This is a dynamic headspace unit with 4 chambers. Simply place a sample into the chamber, close the lid, a flow of gas, which would be typically air or nitrogen, is applied, and the temperature can be selected from ambient up to 250 degrees Celsius. A sorbent tube or DMPH cartridge is attached to the outlet on the top of each chamber, and the vapours from the sample are then swept onto these. If using sorbent tubes, we perform analysis using a thermal desorber GC or a TD-GCMS, or we would use a HPLC when we're using DMPH cartridges for analysis of formaldehyde or other aldehydes. Sampling is really convenient and fast. You can simultaneously collect up to 4 samples, which makes a microchamber ideal for rapid screening and assessment of products. And there's also published examples where the microchamber has been connected directly to a TOF mass spec for instant analysis of very volatile organic compounds such as formaldehyde. There are 3 methods of sampling using the microchamber. Probably the most common is the bulk emission testing, where we place a sample directly into the bottom of the chamber, and we can use that to define a concentration in micrograms per cubic meter or micrograms per gram. Now, flat or planar materials can be cut to a specific diameter of 64 millimeters and placed on spacers that allow us to accommodate for materials of different thicknesses. These samples are then raised up in the system so the lid closes down directly on the surface, creating a surface-only emission parameter. The emissions from these are calculated in micrograms per meter squared per hour and then can be extrapolated to predict the emission rate of larger samples. The third sampling option is for the permeation of chemicals through the sample material. Now, in this option, the barrier material is placed onto the permeation accessory and a suite of compounds can be injected into the well just below this. The lid of the microchamber is closed and the sample tube is replaced at varying time increments to determine when permeation through our barrier material occurs. A critical consideration of any TD analysis are the sorbents used for capturing these volatiles from our test samples, and these can vary depending on what volatiles we're analysing. Very volatile organic compounds require strong sorbents to retain them, whereas the semi-volatile organic compounds can be retained by weaker sorbents. Typically, we have a variety of volatiles that we want to analyse from a sample, so then we need to use multiple sorbents within our sorbent tube to capture this full range. These multi-bed sorbent tubes are also ideal if you're not really sure what volatiles you're expecting from your sample. And we're able to do this as all Marks TD instruments operate in backflush mode. So just to give you an example of this, if we have our multi-bed sorbent, as you can see in the bottom right-hand corner of this slide, the sample goes on in one direction and then the desorption goes off in the opposite direction. And this is really important because our semi-volatile organic compounds now only interact with our weak sorbents at the front end of the tube and don't interact with our strong sorbents at the back end. Backflush operation is crucial in allowing the use of multiple sorbents to extend our range of volatile organic compounds for TD analysis. When we heat our sample tube in a flow of carrier gas, the analytes are swept off our tube onto our electrically cooled focusing trap, and that's held between ambient and down to -30 degrees Celsius. We do have the option to recollect the inlet split from our original sample tube at this point. Once our sample is on our focusing trap, we rapidly heat up our focusing trap in a reverse flow of carrier gas, our backflush operation, to transfer all these analytes onto our GC column. Again, we have the option here to recollect this split, known as the outlet split, which is useful for archiving or method development, as if any compounds exhibit a lower than expected recovery or relative to the split, this would indicate poor desorption efficiency. When running any analysis, there are a few things that can be done to minimize the variability in the sampling and analysis to ensure more confidence in our results. For example, when using the microchamber, careful preparation of samples, using gloves, make sure samples are cut with clean tools. If samples are stored prior to use, then ensure they're packaged carefully. There are standard methods which outline these parameters depending on the material. So if you'd like any details of these, please reach out and we can share those. The use of certified reference materials is something that many using chambers of all sizes would like to have. A material that emits a known concentration. Again, if you're interested in this, let us know and we can help point you in the right direction. Injecting the clean sample tube with a surrogate, such as deuterated toluene, prior to sampling from a chamber or any other environment really, can be used to identify if there are any issues when sampling. Correct capping of tubes is key when shipping tubes to stop any environmental contaminants diffusively sampling onto the tubes. So recording temperature and humidity in transport, and always sending shipping blanks if the samples are to be transported. Using calibration loading rigs for accuracy when injecting standards onto sorbent tubes, and be sure to only inject 1 microliter onto sorbent tubes to negate the solvent effect. In addition, you can inject a standard into the 4 chambers so you can compare the results of all 4 chambers to ensure that they're behaving the same. Finally, as an instrument check, you can use commercially available pre-filled check standards or CRS tubes, internal standard addition. You can utilize recollection or enter proficiency testing schemes to validate your data further.
Thanks, Aaron. Okay, so now let's have a look at some case studies, and we're going to start off with chemical emissions from products and materials that are regulated under global compliance. So there are various different standards out there for product conformity, for indoor air quality, in vehicle air quality. And this looks at all the materials that you may find in your home or in your car that affect the air that we breathe within those environments. So you can see here we've got anything from the European Commission regulation, the construction product regulation, that looks at materials such as carpet, paint, flooring materials, and regulates about 200 different compounds that are emitted from those. Individual countries such as Germany, France, Belgium have their own standard methods that are used for putting labels on materials. And you can see down in the bottom corner that we have rating symbols that are actually put on materials so that when you go to a home improvement store, you can buy materials that are low emitting. In addition to the testing of chemical emissions because of our concern for human health, there's a lot of work also done for off-odor analysis and the comfort of the occupant of these environments. And so a lot of analysis is also done for non-regulated compounds as well. So let's look at our first case study. What we have here is an example of using the microscale chamber for product development. This was a sample of flooring that a manufacturer was having trouble with complying with regulations. So if we look at the information in front of us, we had the sample, which is shown in the top black trace, which was a piece of flooring material that had no lacquer treatment and no heat treatment. And what the manufacturer thought is that perhaps the lacquering and the heat treatment would be able to reduce some of the emissions of volatiles that were regulated. So in the first trace, we can see that we've got quite high levels of phenol and also BHT. And these are 2 compounds that are regulated within the relevant construction regulations. So the sample was then lacquered, and during that lacquering process, the emission of phenol and BHT were both reduced. However, that lacquer did add additional concentrations of butanoic acid and also 2-ethyl hexyl acrylate. So the third sample that was tested was the flooring sample that had been lacquered and then subsequently been heat treated. And during that heat treatment, there was the reduction of phenol and the BHT, which were needed to bring it in line with the regulation, and also a reduction of that butanoic acid and the ethyl hexyl acrylate. So that allowed the sample to then fall within the relevant regulation limits. And this is where the microchamber is great. All these different samples taken from the production line, and then they can be sampled simultaneously from the microchamber over a relatively short period of time. Next, we can look at a different type of material that's used in buildings and affects indoor air and in-vehicle air as well. And this is an adhesive. Now, here what we're looking at is the difference between the cured adhesive and the uncured adhesive. So this is the process that happens over time once the material is applied. So really we're simulating the real use of this product. And it's clear from the data that that curing process causes a reduction in the level of octane, but an increase in the emissions of those long chain hydrocarbons. And really it's this ability to compare samples before and after processing that allows manufacturers to optimize that curing process and to minimize the chemical emissions from the end product. Now, the microchamber allows that, but also the reason that we can simulate that curing process is by elevating that temperature, and therefore we can simulate that product application. And we can also look at simulation of how that product would be used in a normal application. So for example, in a vehicle on a sunny day, that temperature would increase even further. And that demonstration of temperature on this product can be seen on the next slide. Here you can see the comparison of the uncured adhesive at 26 degrees, which is that black trace on the bottom, with the uncured adhesive at 40 degrees. So again, just showing that big difference of emission range over that 20-degree difference. Now, these adhesive emissions were sampled via the microchamber onto a sorbent tube, and that sorbent tube was packed with Tenax TA, and it was analysed using thermal desorption GCMS. We saw earlier in the presentation how we can place a planar piece of material inside the microchamber, and this allows us to eliminate a number of volatile compounds that are released from the edges of materials that may not have an effect on the environment that it's going to be used in. So here, for example, is a piece of flooring material or a coated polymer that is placed into a microscale chamber, and what we have is the top trace is not using that surface emission parameter within the microchamber. So this is just placing a piece of material in the bottom of the microchamber and doing a full bulk emissions profile. And then in the bottom trace, the blue one, what we've done is cut out a sample, raised it up inside that microchamber, closed that lid down, and given us that defined surface area that we're looking at. And in doing so, you can see that we have removed the emission profile of all of those compounds with the orange dots that we saw in the bulk emission. Now, this is really important because if you're being regulated for a material that has multiple layers and you're looking at the effect that it has on the environment that it's applied to, then in this case, we don't want to know what's coming from the back of the material or from the sides of the material, just from that surface. So in addition to the traditional VOCs that we're looking at from materials and products, we now have a whole new class of compounds that have clearly become of great interest to everyone, and that is the PFAS compounds. These compounds are per- and polyfluoroalkyl substances. Their manufacturing began in about the 1940s, where they gained a huge amount of popularity for their resistance to heat and staining. The problem is that those properties that made them so attractive are also the ones that make them really problematic. PFAS are now considered one of our most concerning environmental pollutants, and they've been associated with different types of cancer, developmental toxicity, and immunotoxicity. So currently there is a huge push both within the regulatory agencies and the standardization committees to harmonize standard methods and regulations for the removal of PFAS from many different materials and products. Now, with that in mind, we need to have a look at various different ways that we can analyze and test them. So let me show you some case studies that we've been working on there. So I just wanted to show you a little bit more on the types of species of compounds that we're looking at that are listed within this very broad term of PFAS. And these compounds all contain this fluorinated tail, or this organofluorine that has multiple fluorine atoms attached to the alkyl chain. And we can have carboxylic acids, or we could look at some of the fluorotelomere alcohols, some of the sulfonamide compounds, as well as some of the acrylates as well. And you can see here that there's a wide range of compounds of interest that people are looking at. So in this case study, we are looking at new coat smell, I guess is the best way to describe it. We looked at some waterproof clothing for children that we bought online, and wanted to see whether or not something that we bought straight out of off the internet would have these kind of compounds, and it does. Immediately what we did was take 0.7 grams of coat and we placed it into the microchamber, and we tested it at both 21 degrees and at 30 degrees. And what we were looking for were the various different types of PFAS compounds. And you can see there at the bottom the ones that we managed to identify, and then we determined those as an emission rate, either a nanogram per gram, so an emission rate of mass of compound of interest per mass of sample that we were looking at, or as an emission rate, so looking at the nanogram of the concentration of the compound compared to the time that we were looking at there as well, so a nanogram per gram per minute emission rate. In addition to concerns about health effects, volatiles and semi-volatile organic compounds can also cause concern for the capabilities of a material or a product. And this is primarily seen in semiconductor and cleanroom applications. So the presence of volatiles and semi-volatiles can adversely affect both the growth and performance of the silicon wafers, but also the performance of things like the microprocessors, data storage, and other parts of these electronic components. The compounds that seem to affect this are acids, bases, condensables, and dopants. And these dopant atoms can change the ability of a semiconductor to conduct electricity. Sources of the VOCs that affect semiconductors is actually the materials that the clean rooms that they're manufactured in are constructive of. So there are some regulations and standards for the quality of that material. And one of the methods shown here, this is a German national method, utilizes the microchamber with an elevated temperature of 90 degrees to force those emissions, so that we're looking at this very low emitting material. And it gives it what's called a clean room suitable material standard mark. And this gives it manufacturers an understanding to be able to choose the lowest emitting material. In addition to testing the materials used for the clean rooms, we also need to have a look at product emissions for quality control. So here what we have is some traces of a printed circuit board analysis. So the traditional methodology for looking at printed circuit boards is using a Tedlar bag. Now a Tedlar bag is like a large non-emitting plastic bag which a piece of material can be placed inside. And a flow of gas is applied and a headspace is created, and then that's drawn onto a sorbent tube. Now in this application it was typically run at ambient. And the problem is that a lot of the compounds of interest are the more semi-volatile compounds. And they tend to get stuck to the inside of these Tedlar bags. So what we then did was take replicas of that sample and pop them into the microchamber. Even at ambient temperature, which is the second trace up from the bottom, you can see that there is a much better recovery of the compounds of interest. And if we elevate those temperatures, as you would expect, a higher emission rate is taken from those pieces of material. So you can see here just the ability to utilize the microchamber across a range of product conformity applications.
Thanks, Caroline. So, slight change of tack here with odor samples, but this just shows the versatility of the microchamber with these samples. In this instance, we've looked at cheese, but the principle is the same for other odor samples. Cheese varies loads with differences in not only the texture, but the aroma and also the flavour. And there are various factors that are involved in the nature of this final cheese product, and they include the type of animal the cheese is from, that animal's diet, the processing of the milk, the cheese culture, and the aging conditions. And in addition to this, we've got natural flavourings or moulds that might be introduced to the cheese to give it that distinctive character. Food VOC profiles in general are a challenge as they often contain compounds spanning a massive range of concentrations. We're talking greater than 6 orders of magnitude in some examples. And our relationship with volatile components is quite a peculiar one, really. It seems we've evolved to have a widely varying odor threshold for different compounds. So trace level aroma compounds where we have a very low odor threshold right down to part per trillion levels can have a disproportionately large effect on our perception of an odor or of a food. From a GC perspective, this is a challenge. We need to measure not only trace level but also high concentration compounds from the same sample. Now, one approach to this might be to introduce a concentrated sample to our GCMS system. This would obviously enhance the response of our trace level compounds, but the more abundant compounds are likely to exceed the capacity of our column, and that's going to end up with us overloading our column and overloading our detector. To avoid overloading our column and our detector, and also to avoid the need to run 2 separate extracted samples, Mark's recollection technology allows us to run a single sample twice. First of all, the sample's dissolved in a high split, so a small sample volume is sent into the GC, allowing our high concentrated components to be analysed without overloading our analytical system. The remainder of that portion is recollected onto a fresh sorbent tube and then desorbed as before by using a low split. So then we're going to send a higher proportion of our samples to the GC. And this allows us to look at the trace level components and allows us to identify and quantify these trace level components. The high-low technique is shown here with the analysis of extra mature cheese. So in the high split, as shown here, we're sending a small portion of our sample to the GC, with the majority of the sample automatically recollected. Here we can see that the fatty acids are the predominant feature of this cheese. Here in the low split operation, you can see how we get to identify and quantify the trace level components. Now, an additional feature of the chromatograms obtained here in the high-low analysis of the cheddar is a wide range of analyte volatilities that we can capture. We've identified both acetone, which is peak number 4 in this chromatogram, and orthohydroxy biphenyl, which is peak 69, which is a C12 phenol with a boiling point of around about 290 degrees Celsius. Now, this wide range of analytes can be collected in a single tube because both the sorbent tube and the focusing trap are packed with multiple sorbents. And this is only possible because of the backflush operation of the Mark CD systems. Here, the microchamber was used to capture the complete VOC profile released from a 40mm incense stick. Now, I love this case study because it demonstrates the ability of the microchamber to analyse both an unburnt and a burning incense stick, with the results shown here. As you'd expect, many more compounds are released while a sample is burning, which is a black top chromatogram, a result of the heat releasing the more volatile components from the incense stick and the chemical changes taking place upon combustion. Now for something a little bit different, I guess. Most people are hopefully unfamiliar with, we're going to talk about chemical warfare agents. We often show this work because while you don't necessarily deal with these compounds on a day-to-day basis, they're very good at highlighting how to sample and analyze tricky compounds that might be thermally labile or sticky or very reactive. And so we've looked at nerve agents, blister agents, incapacitating agents, and tear gases with thermal desorption. But here we're going to focus on how the microchamber can be used to sample these types of compounds. Using the permeation accessory for the microchamber here allowed us to assess the migration rate of methyl salicylate, which is a simulant chemical for mustard gas, through a nitrile rubber glove. Now, permeation studies generate a lot of information on fabrics or materials associated with the breakthrough time of the chemical through the sample, the incremental concentration passing through with respect to time, leading ultimately to swelling or degradation of the sample. This type of data is very useful, especially for PPE type of materials or protective coatings applied to a substrate to minimize or prevent ingress of a toxic substance. There's a lot of interest in the screening of chemical weapon agents on materials. So forensic analysts, for example, can establish if a suspect has been in contact with any of these agents. In this example, we took two separate 0.11 gram samples of sole from the bottom of a running shoe. One of these samples was kept blank, while the other was spiked with a 10 nanogram chemical weapon simulant standard. Even at these very trace levels with small sample sizes, we can detect the chemical weapon agents.
Well, thank you, Aaron, for covering those really interesting case studies at the end there. And thank you, everyone, for your time today. Hopefully, Aaron and I have been able to show you the really interesting applications that the microchamber can be used for, and really just introduce this very versatile and reproducible instrument that allows this quick, easy sampling of materials for trace volatile and semi-volatiles. And really how that, combined with the power of thermal desorption, allows you to identify these compounds using GC and GCMS. Now, we went through a lot of very varied applications today, and we're more than happy to share more detailed information on each of these short case studies that we showed. So if you have any questions, you'll feel free to ask us now, but if you'd like any further information, I've popped our email addresses here for you. Please feel free to email us and ask for specific information. But now we're ready to take some questions. Thank you very much.
Well, thank you both for that excellent presentation. We now have time for your questions. So the first question we have is, I don't have a Marx thermal desorber. Can I still use the microchamber thermal extractor?
Yeah, I'll answer that, I think, Janet. Yeah, you can use the Marx microchamber for analysis and sample collection for any TD introduction instrument.
That's great. Thanks very much, Aaron. And the next question we have is, how long do you need to sample in the microchamber?
I'll take this one. I hate an answer that starts with "it depends" on your application, but it does depend on your application. The microchamber is a dynamic headspace system. So when you place a sample tube on the outlet, you're immediately collecting sample from the material that you've placed inside the chamber. And depending on what you're looking for, whether that be a quick screening, you can take a sample within 10 to 30 minutes is pretty typical, depending on obviously the emission rate from the material, the temperature at which you're holding the chamber at, and the flow rate. But we also do look at much longer term studies of materials and things we've kept. For example, a rather smelly day in our application laboratory where we kept some bacon in the microchamber for a week to determine when it went off. So the answer is dependent on your application.
That's great. Thanks very much, Caroline. The next question that we'll take is, what is the size and volume of the chambers?
So there's 4 chamber parts, Janet, and the volume of it is 114 mil. So you can just fit your sample into those, or as we explained during the webinar, you can use them to with spacers, so you can just do surface emissions.
That's great. Thanks, Aaron. So let's go to the next question, which is, in the ISO norm of VOC microchamber testing, it is stated that the edges of the flat samples can be covered with aluminium foil to only test the top of the sample. Is it necessary to use spacers for better reproducible results, or is the aluminium foil enough?
Yeah, this is a really good question. So the use of foil is absolutely what's stated in a couple of different ISO methods. There are probably about 15 different methods via ISO, CEN, ASTM, utilizing microscale chambers, and they vary in their recommendations. Some of them are specifically for material emissions from surface, and they do recommend utilizing the spacers. You've mentioned it in your question. The only difference really is the reproducible nature. So because the chambers are uniform, the lid, when it closes down on that surface area for this instrument, gives you a very defined surface area. I think it's, if I remember off the top of my head, 24.6 centimeters squared. So you are continuously getting that surface area, and the headspace volume above the sample is always identical. Now, clearly, when you put foil around a piece of material and place it into the bottom of the chamber, the surface area is dependent on who's put the foil on, and the headspace above is dependent on the thickness of the material. So there's a little bit of variability there, but absolutely, you are fine putting foil around. It just takes care and attention.
That's great. Thanks, Caroline, for that. So our next question is, are there any regulations for PFAS emissions?
This is a really big topic, and I could probably do a half-hour presentation just on this, so I'll try and keep it really brief. As we're discussing here, we're talking about PFAS from materials and products and an indoor environment. So I'll leave the ambient air side of it out of this discussion. But specifically for indoor air and materials, there are 2 documents in draft at the moment that we're part of the committees on, which are in ASTM, the American Standard Agency, although it is a global organization. One is specifically based on thermal desorption, GCMS of 4 fluorotelemers. And these fluorotelemers are compounds that cannot be analyzed by LC. And I'm going to combine a couple of questions because I saw a couple of them pop up. So a lot of you asked about, could we just use LC for these compounds? Well, in this case, we're looking at trace volatiles in air, whether that be indoor air or whether that be chamber air. And for those applications, you need to use a pre-concentration device, so this thermal desorption, and you need to be able to look for non-targeted compounds, including these very small chain compared to most PFAS, and this broad analyte range, which is why it lends itself so well to thermal desorption GCMS. So we can look at those VOCs and SVOCs in one run sampled onto the sorbent tube. There is a whole other application that we can talk about offline if anyone's interested, looking at canister-based or online analysis of the more volatile PFAS compounds. So within this, we use a specific sorbent tube that has multiple adsorbents in, and this is a combination of porous polymers, graphitized carbon, quartz wool to expand that range, just as Aaron mentioned about using those multi-bed sorbents, multi-bed trap, to expand that range of analytes that you can take onto the sorbent tube.
Well, thanks, Caroline. Thanks very much for addressing that question. And we'll take the next one, which is, can you run the microchamber at ambient temperatures, or do you need to heat it up?
I think this is probably one of the beauties of the microchamber is that you can actually run it at ambient temperature, but you have got the ability to heat the chambers up to 250 degrees as well to encourage your semi-volatiles to get into that headspace that Kaz has talked about there as well for sampling.
That's great. Thanks, Aaron. So the next question is, when we work with higher temperatures in the microchamber, does the adsorbent tube heat up?
Yeah, this is a really good question that follows on from the previous one. So the versatility of the temperature of the microchamber is for simulating real world environment at room temperature, or for example, in the automotive industry, we run the samples at 65 degrees to simulate a hot day in a vehicle. For clean room materials, we push that temperature up to 90 degrees to really force that emission, but we can take it up to 200, 250 degrees for a kind of a really, quite often to simulate production or formulation capabilities. And in this case, you do have to be a little bit careful about the length of time you would leave a sorbent tube on what is an elevated temperature. However, the microchamber itself has small little fans on the top. So when you elevate that heat, we do have a fan that will draw the lab air to blow over the outside of the tube to try and reduce that temperature. But we do tend to recommend short sampling times when you're running the microchamber at very high temperatures. The other thing that we can look at there, sorry, I just suddenly thought of something else. The other thing we can look at there is the strength of the adsorbent material inside the tube for the compounds that you're looking at. And if you have a specific application, please just drop us an email and we can give you some much more specific suggestions for that application.
Thank you, Caroline. So we'll take the next question, which is, are the microchambers reusable? I'm thinking about the adhesive sample. How do you remove this from the microchamber after use?
I think there's probably a couple of questions about this, so this will hopefully answer a couple of questions. Certainly, the microchambers are reusable. You can take the pots out to the microchamber and give them a good clean, and you can test to make sure how efficient you've cleaned your sample by running them as a blank and collecting onto a tube to make sure they are fully clean. But we do also do aluminium trays or boats that you can put your sample in, especially if, like you're saying, if they're particularly a sticky sample like an adhesive, then you can put them into the aluminium tray so that you can heat up, and then you can dispose of the aluminium tray after you've used them.
That's great, thank you. So we'll go to the next question, which is, how does the microchamber compare to the large chamber analysis?
So there are multiple different sizes of chambers, and most of them are specific to a certain application. So construction product regulations, vehicle interior air quality run standard methods for microscale chambers, small chambers, which aren't actually that small, they're about 1 meter cubed, and then large chambers, which tend to be the size to be able to fit an entire vehicle in or an entire piece of furniture. So what we have here is the difference between component testing and full material testing. So you can predict the results of a small chamber, for example, a 1 meter cube chamber for certain materials by sampling for the microchamber. You'll be able to tell whether or not a material would pass or fail a standard regulation for a small chamber. But obviously you can fit a much larger piece of material into a small chamber. For example, if we looked at a piece of furniture, a chair, which is got leather, foam, wood, adhesive, then clearly you're going to get emissions from multiple different materials. Whereas the microchamber, you could break that down and identify any concerning emissions or emissions that were over the regulated amount, which aspect of that chair they had come from. So you can use it to screen materials prior to analysis in some of the certification regulations, or to predict the results from those.
Excellent. Thank you, Caroline. The next question we have is, the trap can be worked from -30 to 0 degrees C, but how can I know at what temperature I should work, and what does it depend on?
Okay, I'll take this one. Yeah, actually, the trap can be used from -30 up to room temperature. So what we're talking about here is once we've taken our sample onto our sorbent tube and we place that sorbent tube into our thermal desorption system, we heat our sorbent tube up, and in a flow of carrier gas, we take all of those compounds that we've sampled onto our sorbent tube onto our focusing trap. Now, the general rule of thumb is that the sorbents in the trap should be the same as in the tube. And if we can trap it on the tube at that room temperature or elevated temperature that we've taken the sample onto, then the trap is typically held at the same temperature. The use of a focusing trap being at a below ambient or even sub-zero temperatures is more for the applications where we're looking for very volatile compounds. And a lot of our instrumentation we use for very volatile compounds from ambient air or from other applications. So we would draw the sample directly onto that focusing trap. And in that case, we tend to hold our trap at those subambient temperatures. Again, if that person wants to email us and tell us exactly what compounds they're looking at, what application, we'd be happy to give some much more specific numbers to them.
That's great. Thanks, Caroline. So the next question is, you assumed that all compounds of interest get out of the chamber to the tube. How can you be assured of this?
So I think there's two questions here, so I'll try and answer both. There's two different things that we want to think about, which is, are the conditions of the chamber simulating what you want to understand from the material? So if you take a piece of material, put it in a chamber and sweep the headspace of that material onto a sorbent tube, then you are on that sorbent tube, it will give you the information of what is in that headspace. Now, if you are looking for something that is not emitted at room temperature onto a sorbent tube, you can look at actually a really good method is ASTM D7706, which is a guide about how to use the microchamber for material testing. And in there, what it talks you through is the incremental increase of temperatures so that you can identify the profile of your material over a range of different temperatures. So for example, if you're looking for a specific compound that you don't want to be released from your product, or an odorous compound that you're concerned about, then you can do these different types of aspect. Now, what I think might also be the question here is, what about compounds like some semi-volatile or sticky compounds that are renowned for having what we call sink effects, where if you put a material into the Tedlar bag I mentioned, for example, for the semiconductor application, or perhaps the larger chambers, these semi-volatile compounds can emit from the material, but stick within the environment. And that's really where the microchamber is such a unique instrument, because it has such a low surface area. Especially if you raise that sample up with those spacers, then you're just minimizing the concern of sink effects. So the other thing that it might be asking is, often what we suggest is to pop a sorbent tube in series when you first start analyzing, to make sure that you don't have any breakthrough of compounds if we're talking about the complete other end of the spectrum of the very volatile compounds. So you want to make sure that nothing is broken through that initial sorbent tube so that you're getting quantitative analysis of your compounds.
Thanks, Caroline. The next question that's come in is, which column was used in the GC for the incense stick analysis?
That was a standard, a fairly standard DB5-like column. We've got the dimensions of that as well, Janet. So if you share with us who's asked that, I can share with them the application note on that, which has got more detail on the exact column.
No problem at all, Aaron. So the next question is, can you please tell us how we can remove water for stronger sorbent tubes without affecting the VOCs on thermal desorption?
So with the XR range of TD instruments, then they can operate in something called an elevated purge mode, where you can actually, when you're doing your water purging, you can actually heat the temperature of that purge to remove water without removing any of your VOCs.
Excellent, thank you, Aaron. So we've got time for another question, which is for the flooring industry, how do you need to do the sampling and the storage before testing?
Yeah, this is, some would argue, more important than the actual sampling and analysis is how you store your piece of material prior to the analysis. So for the flooring industry, I presume that that most people are complying with what we call the construction product regulation, which is the European regulation, but is replicated all around the world, which is where you take a piece of material and you would place it into a small chamber for 3 and then 28 days to simulate application of the material by the construction team, and then the reoccupancy of a home once it's been made, or an office or a hospital. So in this case, there are very stringent rules within that regulation, and I will share the document with the person who's asked this question. But basically, it's all about when you take it off the production line, as soon as you take it off the production line, how is that material handled? It's placed in a non-emitting sealed container. It's placed in a temperature controlled environment. There is a certain time period that's allowed to pass prior to the sample being analysed. So I'll share that document with the relevant person.
That's great. Thanks, Caroline. And I think we'll take one more question, which is, you mentioned that no more than 1 microliter should be spiked as standard. If, for example, methanol is used as the solvent, it shouldn't have any effect if more is spiked. Is that right?
This is an interesting one. So in short, there are some concerns. So when you inject a calibration standard, let's say, onto a sorbent tube, you have either one or multiple compounds that you've dissolved in methanol, and you draw that methanol onto a syringe and you would add it to the front of the sorbent tube. We would always recommend that you do this using what we call a calibration solution loading rig. So what that does is then it purges the methanol from the tube whilst retaining the compounds of interest. Now, in this case, if you inject a larger volume, you run the risk of some of that methanol not having been purged from the tube. Now, when you place that tube into the thermal desorption system, as I mentioned, what you're doing is very quickly heating that up and passing it through onto your focusing trap, and again, then very quickly heating that focusing trap and injecting it to your GC column. Now, if that volume of methanol is too great, we have what we call a solvent effect, which can shift the retention times of the compounds of interest. Now, it depends when you say more. I mean, if you're talking 1 or 2 or 3 microliters, not such a problem. But there are some older methodologies that recommend larger injections. So we always suggest that 1 microliter and making up different concentration solutions so that you can inject 1 microliter onto tube is the most reproducible way of validating your system.
Well, thank you again. And if any other questions do come in, I'm sure that Caroline or Aaron will be happy to respond to them via email. I'd also like to thank our scientific partners in this webinar, Marks International. And with that, I'd like to thank you all for logging in and listening. Thank you and goodbye.